Hello everyone, and welcome again to the new class. And in this class what we are going to do is to discuss what are kind of orbits actually, and how to decide what kind of orbit particle is going to have when it is under the influence of the central force field. Okay, so to decide this central force field, what you need is some equations we have already derived in our previous classes. One is the radial velocity. That is you can see that this is my dr by dt, the radial velocity. This is equation which is depending upon this E and this L. And so energy is going to have, the particle is going to have the energy, and it's going to have the angular momentum, it's going to have the mass, and then what kind of potential it is going to face when it's coming into certain field of force, because which is derivable from this potential. So this equation basically indicates that if you see that dr r dot dr by dt vanishes at the roots of the radical. This equation, this radical is going to vanish at which point is going to have the two roots. Okay, that is at points for which this inside, that is E minus v minus L square by twice m, this factor is going to be 0, because the mass, this is not going to be 0. So this factor, if this factor is going to 0, this is in terms of L square. So that is when r dot equal to 0. So this is going to have whatever the point r value, it is going to be 0. These are going to be the turning point of the motion. So that means when the particle is in the central field, if it's coming into the influence of the force which is derivable from this potential, so then that particle is naturally going to turn away, either getting because of the repulsion or because of the attraction. It is going to turn at certain position, and that turning point is going to give me the root of this radical, that is where the r dot is, that is the velocity of the particle is vanishing, is 0. So this turning point can have the two roots. This because of the two roots, that is going to be the r maxima and the r minima. These r maxima and r minima, if you recall from the previous lecture, that are going to be the ipsidal distances or ipsidal vectors. That is the distance of the central force of the force center from the turning points. Okay, so the motion of the particle is therefore confined in the annular region specified by some r. So that is going to be r maximum or r minimum. So when you have some r maximum and r minimum, the particle can be within that region, annular region of that. Okay, so with some turning points which is defining your r maximum and r minimum. And then this is if you further analyze this equation, that the certain composition of the potential, because E is fixed, angular momentum you can choose, mass is there, the particle, so VR is going to play a very important role. So for the particular combination of the potential and the parameter E and L produce only a single root. Okay, so there may be two root, and then you can have only one root. So in such case, that r dot is 0, where you have one turning point, so that is dr by dt is going to be constant. Okay, so this r is constant, so that means dr by dt equal to 0. Okay, so that is r is going to be constant. R is going to be constant, so that the orbit is going to be circular, because only the circular orbit is going to have the constant one. Okay, constant distance from the so if you have a center of the force is here, the particle is doing a circular motion with the constant r along this force. So this particle is center of the force, and this is doing a circular motion around this. Okay, so for particular potential and particular combination of ELN, if you're going to have one root, that is r dot equal to 0, then the particle is naturally going to have a circular motion around that. Further, if the motion of the particle in the potential is periodic, okay, then the orbit is going to be closed. So periodic means that means if the particle is coming and going and then coming again to the same position, so that is why it is periodic. So that if the potential motion of the particle with particular potential is periodic, then the orbit is going to be closed. That is, after a finite number of excursion between the radial limits maxima and minima, the motion exactly repeat itself. So maybe it can repeat itself, or like it do one complete it. Okay, like in this figure, if it start from here, so this is the force field, and then this particle is from here somewhere, you have the center of the force. The particle is coming here, and then it's going here, here, and then this is maybe somewhere it is going to close within this region. Okay, or it may not going to be closed. It can have this motion. So but if the orbit does not close on itself after a finite number of oscillation, the orbit is said to be open. Okay, because you see that, let me it may happen that if I have some region where the particle enters, and then after doing certain, and this is going to close, and it is repeating itself, the motion is being repeated. Okay, but it may happen that if I have the, like in this region, if my happen that I have a region that is going to be R maxima and R minima in this region, if the particle is in this region, and this there may be no close, the particle is not getting close. If it insert in this region, it is going to have reflected back, and then it is not going closed. So it is within this region, but it's not getting closed. Okay, so one closed orbit is this, but like in between R, when we have two roots and the particle is constant to be in the annular region of R maxima and R minima, then we're going to have either the trajectory is going to be closed by repeating itself periodic motion, or it is going to be open. Okay, so one is like close, then it's going to be circle, depending upon if I have one root of that radical part, and then it is going to be either close or orbit when you have the two roots. So the motion is within certain region of R maxima and R minima. Okay, so now okay, yeah, I already have this. So this between R1 and R2, so you can have this. So particle is going to be like particle enter, this is the center of force center, and then between R1 and R2, R maxima and R minima, you're going to have this particle is the trajectory of the particle is closed. Okay, and it may not be closed. The second thing is for the theta, that was on the basis of the radial velocity, but this part is very important, whatever equation of motion or integral you are dealing with. So here if you're talking about the theta depending upon the r, so from this equation we can compute the change in the angle, okay, that results from the one complete transition of r from r minima to r maxima. So on the basis of that r radial velocity component, that we decided that it's going to be either going to have one root or going to have two root, that is r maxima and r minima, and from there I can decide in the reverse that what are the angles corresponding to that through which this come under the complete transition between r maxima and r minima. So because the motion is symmetric in time, this angular change is twice that which would result from the passage from r minimum to r maximum. So that's why this is going to be twice time between r minimum and r maximum. This is going to be the twice. Okay, so the path is only closed if delta theta is a rational function of 2 pi. So you see that when you correlate with this concept of r maxima and r minima, and the close and open within the some region of r maxima and r minima, that you certainly needs that this is going to be delta theta, the change in the angle is going to be 2 pi times some constant a and b, where this a and b is some integers, So whatever the periodic motion, the b period, the radius vector 2, radius vector is like your my r maxima and r minima 2, and then you're going to have the complete revolution and will have returned to the original position. Okay, so that is a times going to be uh, the complete revolution. So this a is here is going to, this a complete rotation it will do for this uh, b periods of radius vector. So nevertheless, you see, because starting from the differential equation that is the trajectory is invariant under the reflection about this epsilon vector. So that is when you change theta to minus theta, the system, the motion is going to be symmetric. So the angular change is, that's why the angular change is twice of that between r maxima and r minima. Okay, so and this is the last thing which I want to discuss today, is that which is very important to decide under certain potential, when we plot the potential and we decide what kind of energy is going to be. So this is centrifugal energy and the effective potential. So whenever you see that R expression of r dot or theta r, this is the common expression. So even if we see that theta r, this is the common expression, and similarly for the r theta, this was going to be the common term in this all these expressions. So in this expression, look at for this L square by 2 mr square. This term has a dimension of energy, because everything is energy. This is total energy, this is potential energy, and this is definitely is going to have the dimension of energy. And according to the relation that L equal to mr square theta dot, and this we can write this term, uh, this half L square by mr square is this half is there. Okay, and then L square I can term this m square r square theta dot square. So m square r square theta dot square, so this is cancel out with this, and then half m r square theta dot square. Okay, so if we, how to interpret this quantity? If we interpret this quantity as a potential energy, because ultimately it's going to have the it is having the dimension of energy. So if I say this is the potential energy, say this is defined by some VC potential energy, that is half, this is half m square L square. Okay, so what kind of force this potential energy is applying on the system? So then when you have the potential, you can differentiate it, that is minus time gradient of that potential is going to give the force. So if I differentiate it, okay, so if I differentiate it, so half L square by m is common, then I have del r of 1 by r square, 1 by r square. This is so if we say this half L square by m del r by r minus 2. So this is going to be minus 2 r to the power minus cube. So this is half L square by m. So this is minus 2 r to the power minus 3. Okay. So then this 2 will cancel out, and then you have 1 upon r cube. So this is L square upon mr cube. So this is nothing. If you write L square, if you write L square here, this is from L, this is going to be m square r cube m square r4 theta dot square, and you divide it by, this is mr cube, this one. So this is going to be m, and this is going to be r cube, and r4, this is r theta dot. And what is this thing mr theta dot? This is going to be the centrifugal potential. Okay, mr square theta dot, because centrifugal potential is mr omega squared, and this is going to be omega is basically theta dot is omega is d theta by dt. So this is centrifugal potential. So the force is centrifugal force, so that's why we can say that this potential is the centrifugal potential. This potential is centrifugal potential energy. So because centrifugal potential energy is not the real thing, it's a pseudo potential, which is because of the motion. So in potential, in my energy here, this E is total energy potential, and this potential, what you get is I can write my real potential what we are having, and then L square with this, we call it as effective potential. So I have energy as this is half m r dot square, and then I have this 1 by 2 1 by 2 L square by m r square, and then I have my potential. So this is what I'm going to have, and V effective potential. So this is the potential which we are talking about, but this centrifugal potential is coming into play also. So altogether this is giving me an effective potential. Okay, so V effective R is therefore the fictitious potential that combines the real potential VR here with the energy term associated with the angular motion about the center of the force. So from where it is coming? Because this potential is associated with the angular motion. So because angular momentum is here, so that's why it is associated with the angular motion about the center of the force. So I have a real potential VR, that is inverse square law 1 by r square and proportional to r, whatever it is. But because that particle is moving and that is having an angular momentum, going to have an angular momentum, this effective potential is containing this centrifugal potential. Okay, centrifugal potential energy. So when I have this effective potential, this we have to remember, because on the basis of this we are going to decide what kind of motion my system is going to adopt. So for example, what we are going to discuss, we will discuss it into the next class, but we will going to take that my force is the inverse scalar force, that is this is minus k by r square. Like gravitational force is g m over r square. Coulomb force is q by r square k times. So everything is like 1 by r square. Okay, so this is for which the force is attractive. So once your force is 1 by r square, this is inverse scalar force, the potential is going to be 1 by r. So then if my real potential is k by r, and then this the potential which is coming because of the angular motion of the system, that is because it is having an angular momentum. So the total effective potential is my this. So if the force is acting and the corresponding potential like this, but the effective potential what is on the particle which is acting is minus k by r half L square by mr square. Okay, so I think I'll stop here, and in the next class I'll start from this position that if I have inverse scalar force and the effective potential is acting on the system, so if I plot this potential, I plot this potential, what effective potential I am going to get, and if a particle comes into this potential, and that is so with certain energy, what kind of trajectory is going to have. Okay, if you see that if you plot this my force is minus k by r square, and then I have the corresponding potential minus k by r, and the effective potential is this, as we have discussed here. Okay, so as we have discussed here, the effective potential minus k by r half L mr square. So this is what I'm going to get is so for a particular L value, say L could be anything, and for M is a fix, and particular L and K and M value, if I plot this is so if I first plot this V prime, that is this line that is the real potential minus k by r, and then this potential, this centrifugal potential energy, if you plot for particular L values, and so this comes out to be like this, comes out to be like this. Okay, so what is the effective potential adding this and this? What is the effective potential V effective I'm going to get is this one, this potential. Okay, this solid line, is my effective potential. This solid line is my effective potential. Okay, so let us try to understand what are going to be the trajectories. But before that, one thing is important. This is the total energy of this system. So what kind of energy a particle is going to have? This is the kinetic energy, and this is my effective potential. So this is my V prime in this case, which is have been plotted. So if I take the difference between E and V prime, so E and V prime, this is going to be the kinetic energy. So that E and V prime is going to have always positive, because if this is not positive, then this r dot is going to be negative. Okay, so that velocity cannot be negative velocity, so that is going to be absurd. So this one condition is that E minus V has to be positive. Okay, so keeping in mind that E minus V prime has to be positive, whatever the energy the particle is coming, and depending upon whatever what is the value of the potential, effective potential, the particle is to decide what trajectory it is going to have. For example, we can have three conditions. In this condition, you see that E1, so this is E1 is velocity is greater than 0. This is my 0, and here is the same force center. Here is I have a force center. Another particle is, this is the 0 line, and this particle is coming with the positive energy greater than 0. This is E1. So this, if you concentrate on this line, this is E1. So everywhere this line energy is greater than this effective potential. Okay, this the black curve, effective potential. So that is E minus V prime is always 0. So the particle is coming here from this direction and coming here, and at this position, after this position, this curve is more. So after at this position, so V is greater than E prime. So when V is greater than E prime, at this position you have R dot is going to be 0. It cannot be negative, so that is going to be 0, and then the particle return back to its position. So when the particle is coming from infinity and then coming at this position, this is the one turning point, and this the turning point is going to have distance. This is going to whatever this from here, the center of, so from distance from the center force is going to have, say, r1. So at this distance from the center, from the force center, the particle is coming and it is turning back. Okay, so the particle is coming and it is turning back, and this is the center of the force. Okay, so this distance is your, what is you call is epsilon distance from the distance from the center of the force to the turning point. So when the particle energy is become less than the potential, so then this r dot is going to be 0, and then from there the particles return back towards wherever it is coming, whatever the trajectory it is falling. So, and then you can have the second condition, that if your energy like this here, so the second condition is like E2, when E2 is 0. So the particle is like here, and then when it comes here, all this point it is having an energy which is greater than this potential energy, effective potential. So at this position here, from the center of the force, this r2 will be more than r1. This is r2. This particle is going to have a turning point. Okay, so this is again a turning point trajectory. So in this case, whatever the particle, from where the particle is coming, but this is going to have here a lower bound, that at this distance particle is going to return back, and the upper bound, there is upper bound, no upper bound, and the lower bound is there in this case. Same will happen with this E2 equal to 0. Okay, so then E2 equal to 0, the same equation will be there, but the distance is more. So then means the particle is coming with the more distance from this center. Okay, more distance from this center. So for the next the more other energies, E3 and E4, I'll discuss in the next class, and this is all for today's class. Thank you very much.